I'm standing in front of a Fryer 3-axis CNC milling machine. This is a large machine. I'm standing 10 feet away just to soak it all in with this camera. We'll be examining different parts of the machine right now. This is the spindle where the cutting tools are mounted. This is the part of the machine which rotates. It's all attached to the Z-axis and it can move vertically up and down. On the side of this spindle is a gray handle which releases something called the quill. This black handle moves the spindle up and down when you want to use the milling machine as a very accurate drill press. Otherwise, you rarely use the quill feature. The table of the machine is large. It moves about 30 inches left and right and in and out approximately 20 inches. It has 3 slots mounted on it. A beautiful carousel built by Walter will hold our tools, and here are the 3 T-slots in the table. They're actually inverted T's, and things called T-nuts can be slid into these slots to hold various things down. It is possible to hold parts directly to the tabletop as well as a vise. When you want to clamp a part directly to the tabletop, you would use something called a table clamp. It's attached to a T-nut, it slides into the slot, and it can be used to clamp down an object. You would need at least 2 of these. Keep in mind, it is possible for the milling machine to cut into its own table. There is no safety feature built into the machine to prevent that. The vise is also a very commonly used device for holding objects in the milling machine, and we will be making use of that all the time. In the back of the machine is an oil system which pumps oil to lubricate the ways and bearings of the machine. There is also compressed air used to do tool changing, and of course electricity is the main power source. To turn on the machine, you turn the gray knob in the back and the red knob on the side inside the yellow square. When the machine comes up, the Analam 3000 touch-sensitive liquid screen powers up. It's filled with many user buttons which we will discuss later. One of the first things you'll have to do is power on the servo motors. You first have to make sure the emergency stop is not activated by twisting it to the right. It will pop out, and then you push the servo reset button to reset the servos. At this juncture, you will have to hit the home button, the F4 key, and the homing process will take place. Sped up, you will see the Z-axis goes all the way to the top, the Y-axis comes all the way at you, and the X-axis goes all the way to the left. At that point, the machine will read X, Y, Z, 0. Before describing how to actually move the CNC axes, let's keep in mind that the machine is designed so that the table makes X and Y movements, while the Z-axis makes the up and down movements. Thinking of the table moving around is extremely confusing. We will therefore pretend that the table is stationary and the spindle makes all the movements. With this assumption, the familiar Cartesian coordinate system will remain in effect, and these XY axes can be thought of as being directly on top of the CNC table. In this way, your programming will be made much, much easier. That's a positive X movement. Why? Because the spindle appears to be moving to the right. X negative, Y positive, Y negative, Z negative, and Z positive. To go over the motion of the machine again, and to show you the difference between line moves and rapid moves, we have zeroed the machine on that corner, and it is now going to make a 6-inch rapid move to the right. Positive 6 inches. Why? Because it looked like the spindle went to the right. Thinking of table movement will drive you crazy. That's why positive 2.5. And this is a rapid move back to 0, 0. These moves are made by entering them onto the keypad by selecting rapid and then entering the coordinate you want to go to. This is now a line move from x equals 0 to x equals 6. Remember, the spindle is moving to the right, positive 6. You have to enter a feed rate. Here it is 20 inches a minute. Rapid moves are used to rapidly go with a tool to start cutting, and then you switch to line moves to actually make a milling cut. I'm now going to enter a line move in 3 directions at the same time. You push the line button and up comes the line menu. I'm going to enter x equals 6, y equals 2.5, z equals -10 with a feed rate of 20. Z -10 will bring the z-axis up because it's right now around -16. When executed, you need to push the execute button. The tip of this drill, sped up, will sweep out a space diagonal. It is complex three-dimensional movement like this, which makes milling 3D complex geometries possible. Okay, I just want to show once again using the pulse generator. It's really simple. You click that to the x-axis if you want to move it. With this in 100, every time I move this, it moves 1/10 of an inch. Every time it makes a little click, and you can make very coarse movements with this. If you reduce it to 10, it moves 1/1000th of an inch every time. It's moving very slowly now, and believe it or not, you can move it in 1/10,000th of an inch increments. The same thing is true for the Y. And if I select the Z, I can move it up and down. This is one of the most useful ways of moving the axes. This area here, there are jog buttons. Now, jogging in the middle, there is a button that has a hand on it, and that's for like hand movement, jogging. I'm going to hit the jog button, and every time I hit the jog button, next to the word jog, it says 1. I hit it again, it says rapid. I hit it again, it says feed. I hit it again, it says 110. Now I'm in inches now, and a movement of 1 would be 1/10,000th of an inch. A movement of 10 would be 10,000ths of an inch, and a rapid will just go rapidly. So for example, in rapid, if I hit X positive, it will go positive. X negative, it will go negative. Let me discuss how to remove a tool from the machine. The first thing we're going to notice is the quill on the side. The first thing we're going to want to do is to make sure this handle is up and unlocked, and make sure the quill is all the way up. The tool will not come out unless the spindle is all the way up. Now we're going to just lock this down. The next thing we're going to focus our attention on are these in-out buttons that are located right above the spindle on the left side. Notice there's a green button on the outside and an in and out red button top and bottom. To remove the tool, you push and hold in the green button while hitting the out button. Now you'll hear the air pressure when you do that. Now let's focus in on the spindle. When I hold in the green button and the out button at the same time, the tool is going to come out. I notice that the spindle is dropping there. When the tool comes out, I'm free now to change tools. Now notice, there are notches here, and in here there are also a corresponding set of notches. Now to put the tool back in, you have to rotate this around until it fits into those notches. Then you hold the green button in until the tool is back in there. This particular method of tool changing is called the power drawbar system. It is a manual tool changing method. However, it is fairly quick. And the part of the machine that has the power, this is where it is. The power lock system, that is the part of the machine which does the tool changing. Now, you're probably all familiar with the vise, but this particular vise, it has this handle that opens and closes the vise. It is held into the table with these T-nuts. Again, we're using T-nuts that have threads coming out of them, and the screws are tightened with the same handle as you would tighten the vise with. Chips often get inside a vise, so if you're using a vise, it's very important, if you want accuracy, to make sure the inside of the vise is extremely clean. We do have an air gun mounted onto the side of this machine. Here's the air gun. It blasts compressed air. It's sometimes something, you don't always want to use a compressed air gun, but it can be useful. Do never play around with these in the shop class. Typically, when you use a vise, you would put a piece of metal in the vise like this. However, you never know if the metal is angled this way, or potentially it could be angled this way. And if you want it flat, you use these precision ground pieces of metal called parallels. Now we have sets of parallels. They come in many different sizes. You have to sort of select one that's appropriate to your machining task. And then when you put your piece of metal in the vise, it holds evenly down on the parallels, and you're guaranteed that the top of your material is relatively flat. It's also important that you tap down slightly on a piece of material when you're tightening it in a vise, because sometimes when you tighten it, it can lift up, and it's essential to tap it. If you want to protect the material from the little bang marks that might occur with the ball of this handle, you would put something over it, a piece of wood or something, to tap it down. Okay, I'd like to describe to you exactly the method by which we're going to make these nameplates. We've created a jig to be used in the production of these nameplates, and this is the way the jig works. It's quite simple. This is the bottom part of the jig, and it's going to go into the vise. Now I just want you to take note of how this one corner differs from the other corners, and I'm going to discuss that in a second. But basically, this part of the jig is going to go into the vise, and it's going to stay there for the entire class. The next thing that's going to happen, and I think I mentioned this to you already, is this is the blank. Everyone in your class is going to be given one of these pieces of aluminum. It is approximately 6 inches long and 2.5 inches wide, and it's about 1/2 inch thick. What you're going to do is you're going to tap 2 holes, 1/4 by 28 threads, exactly at 4 inches apart, directly centered on the bottom of this plate. That's the first thing you're going to do. And then what's going to happen is this. You're going to screw your nameplate onto the top of this jig. We'll tighten these screws. Then this particular plate with your nameplate on it will be put on top of the secondary plate, and it will be clamped on or screwed down with these screws. Now these happen to be called Allen cap screws. They take a special sort of hexagonal wrench to tighten them, and you've probably seen them before. And these will be tightened like this. Once your nameplate is down on the jig, these screws tighten below the surface of the bottom of the jig. They'll come down like this, and we will be free to machine all the surfaces of this plate while making your nameplate. So we'll be able to, for example, change the shape of this rectangular block into whatever we want, really. And the only thing you kind of have to appreciate is that to cut all the way around your piece and complete the profiling, we're going to have to cut a little bit into this jig. That's okay, because these screws go below the surface, and they were made to do that. And we won't go too far below, but while we're profiling out your nameplate, we will actually cut into the plexiglass a little bit. Now, the reason why we've made the jig like this is as follows. After you make your nameplate, one of your fellow classmates will want to make his or hers. Now, we will determine from this corner of the jig, we will set our 0, 0 of our CNC machine, and everything will be referenced from the same corner. And therefore, when we take out your nameplate and replace it with someone else's, we will not have changed our XY0, and we won't have to go through the somewhat time-consuming task of re-establishing the corner of the piece every single time we change plates. So that's the philosophy of this jig. Now here are the Allen screws I mentioned that are on the jig. And this is what's going to hold the nameplate down to that upper plexiglass plate on the jig. This is an Allen cap screw. You can tell because it has the hex. It uses an Allen wrench. The hex is in here. And it happens to be what's called a 1/4-28 screw. Now what that means is the screw is 1/4 of an inch in diameter, and it has 28 threads per inch. So if you could count these, there'd be 28 of these per inch. We must tap a 1/4-28 hole, and in order to do that we need to determine the drill needed to make such a hole. We consult the drill chart and see that the 1/4-28 hole requires a number 3 drill. This chart also gives you the actual diameter of these drills. Drills are listed as number drills, fractional size drills, and letter drills. All the information you need is contained in the chart, but the important thing to know is we need a number 3 drill, 0.213 inches. Hard to see on the camera, but here along the shank of the drill there is an actual number 3 that is engraved into it, and I will tell you a lot of guys drill in them. So to check it, I'm going to use a caliper. Now this is a pretty good one. This is an electronic caliper. It's made by a company called Brown & Sharp. They're in the business of making precision measurement equipment. But let me just say, when you pull it open, you see the jaws underneath open up. This one's a digital caliper, so it gives you a digital readout. And we can use it to measure the diameter of this drill. So I'm going to grab the shank, and it's measuring about 0.21 here. You can also measure the tip if you want, and it measures about 0.212. Now drill bits tend to have the caliper out. Let me just go over it a little bit. It can measure the outside diameter down here below with these jaws, and if you look at the top part, that can be used to measure the inside diameter. On the other side of the caliper, as I pull open the jaw, this rod comes out the bottom, and that can be used to measure the depth of a hole. So this little device here, and this might be how you would use these outer jaws to take an inside diameter measurement. Okay? Now I have to tell you, it's not a trivial measurement to make. It's very easy to hold the caliper crooked this way or that way. It's very easy to measure the diameter here instead of right in the diameter. So it's always a very tricky measurement when you measure inside diameter. So I'm just going to point that out to you. When you're making your inside diameter measurements, you have to be extremely careful. The outside ones are a little bit more straightforward. It's easier to get the outside one right. And of course, the depth of a hole could be measured by coming in, bringing this down, and on a flat surface you could make your depth measurement like that. To prevent oil from being constantly pumped into the machine, we should turn off the servo motors by pushing Big Red. To write a program, you must hit the Program button, and then hit the Create button, and then the ASCII key. And up comes a little ASCII touch-sensitive keyboard, and you can type in a name of a program. I am typing in the name Drill. After typing it in, you hit ASCII again, and when you hit Enter, you will notice that on the screen will appear your new program, Drill.m. You must select it with the F6 key, and then hit F4 for Edit, and you can start writing your program. Notice at the very top, the program appears in a very small font size, Drill.m. All these programs have .m's. And below the screen is the last line of all programs, the end of program line. That's sort of a generic line that is popped onto the end of all programs. The first thing we're going to do is hit the number 7 key and select our units. I'm picking inches. The plus sign will toggle between millimeters and inches. The next thing we're going to do is pick absolute coordinates. Again, the plus sign will allow you to pick incremental, but we will select absolute. The first thing we're going to do of any significance is a tool change command. When you hit the number 5 key, up comes the tool change command. We are going to ask for tool number 1, and the M code is M6 for tool change. That will be our spot drill. After making that tool change, I will want to start the spindle spinning clockwise. The M code for that is M3. And after that, I will select the RPM with the period button and select 1000, which is a good RPM for drilling. So slowly but surely our program is starting to form. After selecting the tool, I'm going to rapidly move to the start point of where I want to drill. So my first hole is at x -2 because the center is 0, 0, y 0, and I'm coming down to the coordinate 0.1 in the z direction. We're now in a position to start drilling, so I hit the drill menu, and I'm going to select the kind of hole I want to drill first. That is the way this philosophy of this machine works. I select basic drilling because this is a simple spot drill. And there's a little picture that diagrams how the drilling process will go. We're going a depth of -0.5. Our start height will be 0.1. Our return height will also be 0.1, and we'll feed slowly to be conservative at 2 inches a minute. When we enter this line, all the information will appear. The next thing we want to do is re-enter the drill menu, and we will select pattern. Now we only have to drill 2 holes, and I could simply put in the coordinate information of those 2 holes, but to show capability of the machine, we'll bring up the drill pattern menu. And here we are in a position, if we wanted to drill hundreds of holes, but we only need 2. Our first one is at -2, 0. We have 2 holes in the x direction and 1 in the y, and the increment in the x direction is 4 inches. So it's kind of a lot of work for 2 holes, but you get the idea. After entering this command, we are in a position to check to see if we are programming correctly. Now all the information we really need is there. It's going to do the basic drilling described on line 7, and it's going to apply it to the pattern of holes described on line 8 in our program. And again, that's the philosophy of the machine. To check our program, we'll hit the draw button, F2. Once the draw button is hit, there are a couple of options under the draw menu, and one is to select the view, and we will select the XY plane, which is a top view, and the display will hit fit, and up on the screen you can see the 2 holes that will be drilled, one at -2 and the other one at +2. The next thing we must do, at the end of all drilling operations, you must enter what's called the drilling off command. It tells the machine to stop drilling. So that's necessary as well. Now the second hole is almost exactly like the first hole. So by copying and pasting lines and then editing them, it'll make life easier. Now copying and pasting is a little weird on this machine, so you must get into the menus you've just seen, hit the More button, and bring up the mark line. When you enter the mark line, it will allow you to highlight the lines that you wish to copy. This is somewhat of an archaic programming method, but nonetheless it does work. We are going to highlight lines 3 all the way down to line 9, the drill off command. We're going to copy and paste it, and then we're going to edit it for our second drilling operation. You hit More again, and it will bring up the copy command. So we'll select copy next, and when you hit enter, notice it says block saved. Now all we have to do is move the cursor down 1 line, and then we will select the paste command, and all those lines will be pasted above line number 10. So we hit More 1 more time, go down to paste, hit enter, and we have copied the blocks of programming to the next line. So as you can see, you have tool number 1 to the drill off command, and then tool number 1 once again to the drill off command. We're going to enter line 10 so we can edit it, and we're going to change tool number 1 to tool number 2. Now this will be our number 3 drill, which will be used to drill the hole for the quarter 28. Now everything else is reasonably good, but to show the capabilities of the machine, we're going to, rather than do a basic drilling operation, we're going to use a pecking drilling operation. So I'm going to go to 14 and hit the clear button, and that erases that line. And now I'm going to go back to the drill program, or the drill menu, and this time instead of selecting basic drill, we will select what's called pecking. Now pecking is a cycle that's normally used for deep hole drilling, and the idea is like a bird pecking at its feed. The drill bit will go down to the depth you program it to, but it will do it in little pecking increments, each time bringing the drill out and clearing the chips from the hole. And I'm entering the pertinent information. We're going down -0.375. The start and return height are the same, and I'm going to pick 0.1 pecks. So it's going to peck 3.1 pecks, and then the final peck will be 0.075. So it will make 4 pecks for each hole, which is a bit ludicrous for a piece of aluminum, but again, just to show you the capabilities of the machine. And again, we'll select a feed rate of 2. And basically our entire program is done. Before running our program, it is necessary to obtain the tool offsets. Now when the machine is first homed, the tool that's put into the machine is a fictitious tool called tool number 0. This is where the tool changes are made. Since we are using tool number 1, we now have to switch this to tool number 1. Having switched it by hitting the number 5 button and pushing tool number 1, we have to actually execute this command to make it happen. So we hit the green execute button, and the machine won't move because there was no movement involved, but the tool has been changed to tool number 1. The next step is to slowly move tool number 1 down until it just touches the surface of the piece of material. I'm using a small piece of paper that I am wiggling back and forth as I slowly lower the tool down. When the paper stops wiggling, I know that I have achieved my surface touch. I now look at the machine coordinates. Now this little box here are the machine coordinates. This is what has to be entered into the tool table. You hit the F9 key to bring up the tool table, and in the number 1 line, tool number 1, we must enter the diameter and its length offset. The big coordinate information in the upper left-hand screen, these numbers there, are the part coordinates, but it is the machine coordinates which are crucially important for doing tool offsets. I enter the tool length offset. In this particular example, the two numbers agree with each other, but they typically do not. Now, we must play the same game with tool number 2. So I enter tool number 2 command, and I'll have to hit execute again after entering this information to make tool number 2 come out. Now we must lower the number 3 drill onto the surface of the material, wiggling the paper as we go. You can either use the pulse generator to lower the Z-axis or the jog buttons, but it must be done slowly and carefully. Once this height is obtained, you must enter it also into the tool table. Now notice this Z machine is 16.022, negative 16.022, and the number in the tool table is negative 16.0219. This must be because somebody recently got the offset and it's just off by 1,000th. So we will make it perfect, and we will have completed entering the tool lengths offsets into the machine. Before we can run our drill program, we must turn back on the servo motors. So to do this, you twist the big red knob to the right, it pops out. You will get some messages that will come up on the screen, and you'll have to clear them. And then you hit the reset servo button. And after that, the servos will come on and the oil will start pumping again, and we'll be ready to move the axes and run our program. Before we can run the program, we must zero the X and Y axes on the center of the nameplate. I've lowered the spot drill down to the center. I hit the X and Y yellow buttons and enter 0, and that will zero the XY axis at the center. To run a program, we'll hit the miscellaneous button, and that takes us to the menu that we run the program from. When you see that auto button light up, then you know you're able to run a program. You hit the auto button, and what comes up is press start to execute or manual to cancel. So we are now ready to run the program. We will hit the green execute button. Now the knob next to the big red emergency stop button allows you to crank down or crank up the speed of the pre-programmed feed rates. So every move, whether it be rapid or a feed move, can be cranked far below what it was programmed for or somewhat above it. Now when we turn on the program, the very first thing is a tool change command to tool number 1. Notice that tool number 2 is in the machine, so we have to switch it to tool number 1. After having done that, we hit the execute button. It cranks up the spindle just like we programmed it to, and it's going to drill the 2 spot holes. The coolant has been applied with a squirt bottle. However, coolant can be made to come out of the machine with an M8 code. The next thing is a tool change for number 2. We change up that tool and hit execute again, and the next drilling process will take place. Realize that we're now seeing pecking drill. It's a little bit different. You'll see the drill go up and down several times before completing the depth of the hole. And after it completes drilling our 2 holes, the program will come to an end, and that's all there is to it. It's time now to tap the holes, and to make sure the tap goes in straight, we're going to use this spring-loaded tip. It's going to be put into the spindle, and then the spindle is going to be brought right on top of the hole to help guide the tap. The tap is attached to a tap handle, and we are going to be manually tapping these holes. It is always necessary to use tapping compound while tapping holes, otherwise you stand a good chance of breaking the tap. I should warn you now that when a tap gets broken inside a hole, it is very difficult, usually impossible to remove it. Frequently you have to start the entire job over again. We move the tip right over the hole, bring the Z-axis down a little bit to create some tension in the tip, and that will keep the tap going straight. For tapping holes, the rule is to go 1 revolution clockwise followed by a 1/4 revolution counterclockwise. That 1/4 revolution counterclockwise is done to break off the chips. If the chips continue to pile up inside the hole, that too can lead to a broken tap. Once the tap has been started by this technique, you can finish it off by taking the tip up and just tapping the hole. Once again, when you're a novice at doing this, breaking taps is pretty common, so I'm just warning you, be careful when you tap holes. 1/4 28's fairly large size tap. It's not likely to break, but when you're using smaller taps you have to be even more careful. We'll play the same game on the right side, lowering the tip down, and in a short amount of time that hole is 2 tapped.